Well, good morning, good afternoon, and good evening to all of our attendees, depending on what part of the world you live in. The outline for today's webinar is as follows. First, we will address analytical data management and its current state at most organizations that we speak with. We will also mention some of the trends that are driving the needs to manage analytical data more effectively. As over the years, analytical data in many aspects has been overlooked due to the complexity and variety of the data generated from analytical instruments. There have been attempts over the years to create new ways to manage this data in a more robust fashion, but those attempts have also created their own challenges. ACDLabs has some suggestions on how organizations might manage analytical data on a global scale and which architectures may be best suited in specific organizational environments. We will provide some specific examples, workflows, and functional areas where we have worked to overcome these challenges in the industries we serve, which include pharmaceutical, chemical, consumer products, government, and academic institutions. Many organizations are now engaging us in corporate initiatives to handle analytical data globally, including the ability to automatically capture, potentially curate, and make review by exception a norm. This webinar will provide the listener with potential ideas and areas of interest that may be of benefit to both you and your organization. In 2018, ACDLabs and CNE News ran a survey to determine the state of analytical data management in all different types of organizations. What we found is that even though these organizations had invested heavily in instrumentation, data systems, archiving systems, CDS systems, these organizations still admitted that analytical data collected was not managed effectively. Imagine the most important result of any experiment, the analytical data required to confirm or deny a hypothesis, not being managed effectively. Important data like determining substance purity or identifying the impurities in a manufacturing process is critically important. If this data is not stored and managed, it becomes useless or potentially even what we call dead data. For those organizations that have been successful in managing their analytical data, they have realized that in order to derive the value from that data, it must be homogeneous, organized, and standardized to be effectively used. Now let's take a look at things from a different perspective, the perspective of the pharmaceutical data scientist. Over the last few years, there's been a lot of hype regarding data analytics in pharmaceutical research and development environments, from retrosynthetic analysis and feedback loops to other utilization of such technology. But how and where does one take advantage of these tools like AI, ML, predictive analytics, neural networks, and how does one incorporate them into existing or new workflows and processes? Given these initiatives have to deal with all the different existing legacy systems like LIMS, ELNs, CDS systems, scientific data management systems, chemical registry systems, high throughput experimentation systems, data logging systems, you name it. A plethora of systems, and how do you bring all of that data together? Many of the past attempts at creating and utilizing data within a data lake by analytical tools have failed because of the lack of standardized, homogenized data that they're trying to and attempt to mine. Therefore, as stated, data must be standardized and accessible to support these specific initiatives. But you might ask, why go through all of this? And if an organization can get this right, is it worth it? What are the benefits? By creating the necessary systems to interface, manage, and store all of the different analytical data types and the variety of data and our metadata in a globally accessible way can indeed pay off for an organization. Archiving of data, specifically analytical data, should bring your organizations the following benefits. An increase in the quality of decisions by making all information available in real time. Not only archive data, but recent information as well, allowing for up-to-date decision making. If one can easily query and access this information, they can reuse the information effectively regardless of geography. Think of time saved in rerunning experiments that can't be found. New insights can be gained from historical data, or one can take advantage of the potential merits of reprocessing that data with potentially new or enhanced algorithms or improved visualization techniques. In addition, one can also take advantage of extracting new value from old records via data mining. And this can only occur if the sets of records or information returned is in a format is easily understood, usable, and standardized. Once static data can now be turned into useful live data. The benefits mentioned here are not new. They were extracted from a paper written, published a number of years ago, 12 to be exact. And yet we see many organizations today not being able to leverage their data effectively and thus unable to achieve these benefits within their organization. So I reference here the article that you can find from Anita Paul and Jörg Hagman. Finally, as you can see, there are quite a variety of different analytical data standards that have been introduced to the community over the years. There are almost as many standards as there are analytical instruments. Many of these proposed standards are only suited for one type of analytical data. For example, ANDI, A-N-D-I, was initially designed to support only MS data and was later adopted under ASTM's framework and expanded into what is now known today as the .NET CDF format. ASTM then subsequently in 2003 went on to consider another format to be a standard, ANIMAL, which many of you may or may not have heard of. And then more recently, the Allotrope Foundation has attempted to create another new standard based on their own developed framework for all different analytical data types by proposing a single data format called ADF, an ontology called AFO, and many different data models supporting the individual instrument types called ADMs. The Allotrope Foundation plans to support multiple data models, for example, one for LCMS, one for NMR, and the list goes on, and requiring ongoing updates to include additional terms for calibration, processing, and other workflow-related data manipulations beyond capturing instruments and methods parameters. To further elaborate on this point, to date, only a few ADMs have been published, and the most mature one is for LCUV data. Today, there's clearly no one format that rules them all. However, let us bring your attention to the ACDLabs Spectris format that was made available in 2011. Yes, this is a proprietary format that ACDLabs did develop over the last 10 years. It's not a public format. However, ACDLabs has had the ability to convert data stored in its format into other data formats like ADF or .NET CDF. ACDLabs is an initial member of the Allotrope Partner Network, and supporting the Allotrope Foundation also support the format and data models that will be eventually produced by the foundation itself. We have done various prototyping efforts for Allotrope Foundation members to prove that this is possible. But Allotrope itself and ourselves, Allotrope has released a version, but we have yet to produce a commercial version. If your organization is willing to walk before it proverbially runs, then moving to a .Spectris or ACDLabs format today can prepare you for additional standards of tomorrow. Managing your analytical data in Spectris DB format today will allow you to pursue your analytical data goals. Ultimately, which standards will survive the test of time? So let's review where we are so far. We know organizations are gearing up or have already geared up to take advantage of AI and ML and predictive analytics to support advanced data analytics. However, in order to do so, one must establish a standardized way to ingest and store that information so that it can be extracted in a meaningful way in the context of the experiment itself. And finally, the ability to manage all types of analytical data in a general and useful way is indeed a challenge, even after you've solved the standardization and homogenization of that data itself. So the remaining challenges that we have seen at ACDLabs in implementing such a system include the following. Typically, the types of analytical data archived on the cloud for data access comes with its own specific challenges and issues. The size of analytical data files today can be exceptionally large in the gigabyte area, creating performance issues for both storage and subsequent access. And in those organizations, for example, utilizing Amazon Web Services, even a download, if it's set up, is costly. The initial interpretation of data may be required by an SME, so the data can't actually, flow through to the cloud without some review, inhibiting the automated data capture, or at least providing additional steps in the process. And then combining analytical data with the necessary metadata may not be consistent across all analytical data types or instrument vendors either. And the combination of analytical data with other characterization data, for example, chemical structures or properties, all in context, is also difficult if other data systems are not readily accessible and can be utilized to combine data together to make it available for query and reporting. And then again, subsequent searching and reprocessing, depending on an organization's capabilities, can be very limited. So as I believe the survey indicated, yes, you may have access to the information in a web UI, but it's in a report. You can't actually then maybe potentially process that information or look for new insights. You'd have to go back to the original file or the original instrument vendor and reprocess those files on those instruments. So let's take a look at what key technology stacks would one need and consider to making this happen in a robust and secure fashion. Silent automation, for example, for data capture, interpretation of that data either automatically using algorithms or scripts, or a live individual, an SME. And then searching via metadata, scientific or chemical structure queries. How might one do that? Peak matching, structural data, other characterization data. Again, how do you manage all of that? How do you search on it? And how do you view and report on it? And then ultimately, which applications? How do you view a combination of disparate and different analytical data types? So for example, suppose you want to look at NMR alongside your LCMS or your MS data, or even your UV or IR data. How does one perform the reprocessing? Which data sets, or do you require a subset of data sets? Do you push data to a data lake for additional processing? And then how do you ensure performance for all of these things? All of these existing and remaining challenges will be discussed shortly. But finally, let's consider for a moment the following high-level design of a system that can overcome the challenges we just identified on the previous slide. The design you see here can support all of your labs in your organization, regardless of geography, and any type of analytical instrument or data format. Silent automation can be performed behind the scenes to collect analytical data directly from your instruments, potentially either processing the data according to its data type or passing it along to an analyst for a more detailed look, or perhaps review by exception, or simply archiving, meanwhile correlating all types of metadata and disseminating that information throughout all the various systems that require it. Basically assembling and deassembling the data for the systems in a format that each can recognize and understand, while all the while managing that data in a standard, reusable, live format, all in the context required for future use. In addition, comprehensive reports can be generated, making the data easily available, viewable, and searchable. Effectively, ACDLabs Spectris platform and the database behind it can become the analytical knowledge management hub for your organization. So with that, I'm going to turn it over to my colleague, Hans DB, and let Hans share with you how ACDLabs have supported organizations like yourselves.
Okay, thanks a lot, Mark, for the introduction. I think basically I want to come back to one of the things where Mark has alluded to is the different formats. So there are numerous techniques, numerous vendors, and numerous data formats. And I think we're showing here a list of possible formats. I think this list is certainly not exhaustive, but people will recognize some of the vendors there working with inside their organization. All of these vendors have their own supporting their own techniques. If you look at Bruker, NMR, MS, if you look at Waters, MS, mainly LCMS, basically all these vendors have their own techniques, they have their own data formats, but they also have their own applications. And if you're using multiple techniques in your research, that means you have to master multiple applications in order to work with these techniques. What is happening a lot at the moment is that people are recognizing the value of analytical data, and what we see a lot is that all these techniques are basically being archived in a file share inside the organization, or more and more inside the cloud technology, in order to make that accessible to multiple users. Often they have an application layer or a web server on top of that, so that people can just find the information back based on metadata searches. A lot of people are struggling with, how can we open the file? It's somewhere in the cloud, we have to download it. So how will the data be accessible? Is it secure? Is it safe? Can we give everybody access? Mark alluded also to the CROs working with your organization and basically also collecting data, and is that data accessible? Is that in the same location or not? If they have downloaded the software, sometimes they need to unzip the files and then find the native software, either with the instrument or on your own installation on your own computers, and open the native software in order to look at the data and process the data. So basically, what we hear from end users is that it's all there, it's all in the cloud, but it's cumbersome in order to work with it. It is also lots of data, and I think it's being Mark alluded to the sizes of the data already, but basically in some cases we're talking about a few kilobytes to a few megabytes, but in some cases we even have basically multiple gigabytes of data that is available and that needs to be shared and downloaded and uploaded to the system. What we're doing with Spectrus DB Enterprise Server is abstract that data, put that in a searchable form, and basically let a ACDLabs client, one client, to access all the data software. That means that you could replace multiple software packages with one and put Spectrus in the middle and open the data files and viewing that data. The list is here. It's certainly not exhaustive, and I think you can find the supported formats on the ACDLabs website, or they could be made available on request. So how is analytical data being managed today? As said, companies are archiving the data. They're putting it in a file share. They're putting it in a cloud location as a zipped file. Sometimes they will go to the ELN or the LIMS system or a structure repository to fetch some metadata. Structures could be made available, but in most cases it's not made available. So what are the limitations? So if you have all the files, you can do some metadata searches, but basically that will be very limited. Full metadata is not available. Structural data is in some cases available, in most cases not available as well. And the spectral data will be certainly available, but not in a searchable format. As Mark said, sometimes PDFs or pictures are available, but certainly not the spectral data. Knowing that more and more people are setting up the archives, I think we have been looking at ways to automate the data and put that into Spectrus. And I just want to discuss today two types of silent automation, what Mark was talking about, where we in the background have a process that fetches the raw data, combines it with other metadata sources and combines it with chemical structures, and then puts it in a searchable format so that it's in Spectris DB Enterprise Server database, and that it is accessible from a client. What I show here is the schema where all the instrument types are automatically, and that could be a process that is in place already at the customer side, or that could be where ACDLabs is collecting that data from instruments and then putting it into an archive, putting it into, for instance, AWS buckets that contain the raw data as zipped or unzipped files. Basically, what we then can do, or what companies have done, is to fetch metadata already, connect that to the raw data in the archive solution. And what we have implemented, and we've done several projects there where we went to either the file share or the cloud data, the cloud archive, and then automatically fetch the data and put that into Spectris DB. And in the meantime, we added some metadata, or we added also the chemical structures coming from a structure repository, and linked that with the analytical data. Linking means also that, for instance, we connect the NMR shifts to the protons or carbon atoms at the molecule, or we, for instance, put a chemical structure and link that to a peak in a chromatogram. That information is stored in Spectris DB Enterprise Server, and that's accessible from an ACDLabs client. So what you see now is that with one client, you can access all the data available in Spectris DB Enterprise Server, and then basically you can do your searches, you can make your combinations, and also, for instance, what we can do is combine for a structure an LCMS, a UV, and an NMR spectrum, and make that accessible in one view in the ACDLabs client. In the meantime, people still have the availability of a web server and a customer-defined user interface in order to download the raw data. Later on, I will also show you that we not only abstract the data, but we also keep the link with the raw data. So if needed, we can go back to the raw data files. I'll tell a little bit more about that later on. The second method, and that's basically going from the other side, where we collect the data directly from the instrument and then put that into Spectris DB Enterprise Server. That means that we can make a selection. We can put all in these cases where the archive is built by a company and it's a file share or a cloud archive. Then basically they collect all the data. What you could do here is not collect all the data, but make a selection. And basically, that's what we're doing for some companies, is just selecting the let's say the selected data sets of reference data and put that into Spectris DB. Here as well, we can connect with LIMS systems, we can connect with ELN or structure repositories to fetch metadata and the structures. That makes it accessible in Spectris DB Enterprise Server and accessible from your ACDLabs client to view at all the data types. What we also do is move that raw data into an archive. So that could be cloud or file share archive that is available at the customer side. And then what you see here is we link that back to the Spectris DB record. So that means from your client, you can have access to the abstracted data and the data interpretation that's been done inside Spectris, but you could also go back to the raw data files which are in the archive. And that's what we call silent automation, the second option. Basically that data is first collected in Spectris DB Enterprise, but also then moved into an archive. On top of that, I think we have some tools that when the data is collected and when the data is coming from the instruments, when the analytical data is coming from the instruments and the metadata is coming from the ELN or the LIMS system, and we have a chemical structure, is that we can apply some techniques in order to help you with the verification if the analytical data and the structures indeed match. So one of the examples here is automated structure verification by NMR. So you make an NMR, you match the structure with the NMR, and then you put the results into Spectris DB, making them accessible for either the scientist who has done the experiment or the analyst who's done for instance, analysis of plates and get the results and view those results. So the email can be sent to a scientist. He can see and go back to the database and get the link and see that either the structure he made is really matching with the analytical data, or that the analytical data shows that he might have made something different. For the high throughput experiments, we can show plate views with signs and markers saying that it's a match or not a match, and people can go back and see, pay a little bit more attention to the structures that didn't match, and look at what the issues are there. Another one is, for instance, in LCMS purity workflow. There we have measurements done on different instrument types, LCMS, and then we have a target list of structures, and then we can match the structure with the LCMS spectrum and determine if the compound is pure or not pure, and if the compound matches or not matches the expected target. Also, these data will be stored in Spectris DB, and basically the scientist or the high throughput group can have a view on that data as well. Other applications we have developed, for instance, in process development, is the fact that we can link multiple techniques of analytical data with the chemical structure. This is a screenshot from one of our products. Basically, I won't pay too much attention to that today, but what you could see here is that for this chemical structure, for instance, there is proton NMR, UV, IR, mass spectroscopy, and 13C NMR experiments done. The data is processed in the background automatically, linked to that component in the tree of synthesis or in the tree of eliminations, and basically you can see that multiple techniques are visible in one view for that chemical structure. Another application is for high throughput experiments, where you can see a reaction done basically in form of vials, individual vials or plates, and you can see, click on that well, and then see the analytical data which has been determined for that. And you could follow what reaction progress is, or you could follow purity, or and also here you see multiple techniques: UV, MS, and the mass spectra itself. MS, MS2, basically all the analytical data that has been made for that experiment can be dynamically displayed in the analytical data view. And basically in one application, you can not only plan your experiments, but you can also see the results. Other solutions where we have been using Spectris DB data is in machine learning or prediction interfaces. In this case, experimental data has been collected. It's going into a Spectris database. It's verified, for instance, by an analyst, and then if verified, it's put into a prediction database. And that means that the next time we're doing our verification, or the next time that someone wants to see what the predicted spectrum is, it means that based on additional analytical data that has been experimental data, it will improve the prediction in your next experiment. And also in the verification, if there is a class of compounds which is under the frequency of that type of compounds is not in the current prediction database set, then that means that the next prediction you're doing and you have that compound class added to the prediction database, the prediction will be much better and the verification will be much easier. Next to NMR prediction, we also have some tools in PhysChem, ADME, and Tox prediction. PhysChem prediction, for instance, can help in prediction in chromatography parameters, and that means that by measuring log P's, log D's, but also pKa's, you could improve your chromatography prediction model. And for ADME Tox, also there we have the machine learning capabilities of adding data to a prediction database. That's basically what I wanted to show you today. It's a variety of applications that ACDLabs has developed and projects that we've done, deployments that we've done, enterprise solutions we've created, and helping you in order to manage your analytical data. I think the conclusion and summary is that basically R&D organizations have been struggling for a long time to archive full analytical data. I think storing data in a file share or cloud bucket certainly can improve, and more companies are doing that. But it's at the end, it's not an optimal solution because it's still tedious to find your analytical data, and certainly with all the applications that are supporting the different formats, it's tedious to get the right application in order to open the right data file. The standardization that Spectris has done for analytical data and making it globally accessible is certainly reducing the number of software interfaces for the end users. And it's making certainly analytical data more accessible, and it certainly provides benefits for the day-to-day work, but as we can see with supporting predictions and also exporting the data in order to analyze the data in a more uniform and better way, is helping in future scientific work as well. Normalized analytical data will ensure that the viability for data science projects, and I think that's where I wanted to conclude my presentation.